So in this lecture, we'll look at the method known as Markov chain Monte Carlo, which is the sampling approach that allows us to make Bayesian machine learning applicable to a lot of complex real-world and important problems. So we will begin our discussion by reviewing the basic concepts of Markov chain Monte Carlo, some motivation for why we use Markov chain Monte Carlo, and how the basic algorithm works. And then we'll turn to the primary algorithm that's at the foundation for Markov chain Monte Carlo, which is known as Metropolis Hastings. So the reason we use Markov chain Monte Carlo is that these independent sampling methods, like the rejection sampling that we talked about the last time, and other methods like importance sampling, don't scale to multidimensional problems. And this means they're really not well suited to problems in the real world. They also require finding proposal distributions that are close to the target. And this is very hard to do, as we noted in our last class. So for those reasons, we use Markov chain Monte Carlo. And it's a fantastic framework for sampling from a large class of problems in the real world, difficult problems to solve ordinarily, but MCMC does a very good job. It scales well to the dimensionality of the sample space, and in the next class we'll see the approach to how that works. But for now, let's take a look at the basic idea behind Markov chain Monte Carlo. As we saw with our Monte Carlo sampling, this is also going to use a proposal distribution. The big difference is that a proposal distribution is not just Q of x, but Q of x given x tau. So it's dependent upon the current state, which we call x tau, the state where we're currently at for our sampling. This is the most important thing to understand about Markov chain Monte Carlo, this note. This is a Markov chain that we're producing, and the sampling is no longer independent. So we're violating this notion of independent sampling, and we're actually sampling according to a Markov chain, which, as you know from what we've discussed in Markov chain, means that it's dependent on the current state. The next state depends on the current state. So the proposal distribution, as we saw in Monte Carlo sampling, should be easy to sample from. And the target distribution should be easy to compute, at least up to a normalizing constant. So we typically write the target distribution, P of x, as P tilde of x, where the portion of the original target distribution in P of x that we're not worried about is a normalizing constant, and we call that Z of P. And it may be unknown. So we may not, the distribution may be complex up to a certain point, but we've got to at least be able to calculate the kernel of the distribution. At each step in the sampling process, we generate a candidate, just as we saw before in Monte Carlo sampling. In MCMC, we're going to do this, but now we're going to generate it based upon this conditional distribution. So unlike before, where the generating distribution was the same throughout all sampling, in this case, it's going to depend on the state where we currently are in our sampling process. So that we represent by this conditional. The conditional sampling from x depends upon where we are currently, which we denote by x tau. And we will accept according to the criterion of the approach. So let's look at the simplest of these, which is called the basic Metropolis algorithm, and look at the acceptance criterion for this algorithm. So we've drawn our point, and that's the thing that we're getting from our proposal distribution. But we're going to assume that this proposal distribution in the basic Metropolis algorithm is symmetric, which means that it doesn't matter if we're in state XB, for instance, the probability of going to state XA is the same as the probability of being in state A and going to B. Now, this is a strong assumption that we will quickly relax, but for the moment, let's just allow us to have that assumption. So we're going to compute then this probability of acceptance, and that's the probability that the candidate, which is denoted by XC, given where we're currently at, our current location, which is x tau, is going to be given by the minimum of either 1 or the ratio between this kernel value that we have for the candidate, okay, and the kernel value that we have for the target. So it's going to be the minimum of either 1, which is the maximum a probability can take on, or that ratio. And the way that we decide whether to accept or not, we use that acceptance probability, and we use it within a uniform draw. And that uniform draw basically is between 0 and 1. We're going to draw a value there, and we'll accept that new candidate location, xc, if that ratio of xc to x tau is greater than the uniform value that we drew. Otherwise, we'll reject. Okay, so the acceptance is it's got to be greater than u. So u basically has got to be less than that ratio, or less than this acceptance, which could be 1. And we note right then that if the kernel for the target distribution for the candidate is greater than it is for our current location, then the candidate will automatically be accepted, because that's what that acceptance probability gives us. So it'll be accepted with probability 1 if that's the case. And if the candidate is rejected, then we go back and draw a new sample according to our current location. Again, that's a conditional draw given that current location of a new value for x. Okay, that's the basic approach known as the Metropolis algorithm. Now let's take a look at the Metropolis-Hastings algorithm, which is really the algorithm that we use in most instances in MCMC. The major difference between the Metropolis algorithm and the Metropolis-Hastings algorithm is that the Metropolis-Hastings algorithm no longer requires a symmetric proposal distribution. So that means that the probability of going from B to A, as is shown here, is no longer required to be the same as the probability of going from A to B. So suppose the current state is again x tau. Then we're going to draw a candidate sample xc, and we're going to do it exactly as we did before from this proposal distribution conditioned on the current place that we are, the current state that we're in, x tau. And we will now accept with a probability that's shown here. So the acceptance probability of accepting the candidate xc, given that we were in x tau, is going to be the minimum, again, of 1, because a probability can't be greater than 1, or the ratio. Now look at the ratio here. What we've done is we've got the same ratios we had before, x candidate, okay, xc over x current location, tau, but now we're multiplying it by the proposal distributions. The one proposal distribution in the numerator is saying, well, suppose we were at the candidate and going back instead to where we're currently located, x tau. So it's looking at that direction, and the denominator is looking at the actual direction we're in, which is going from x tau to the candidate. So this is our acceptance probability. And again, we'll decide if we accept by making a draw from a uniform distribution between 0 and 1. And if that uniform draw is less than this acceptance probability, P of xc over x tau, then we accept. And if it's greater than that, we reject. And in a similar fashion to what we saw in the Metropolis algorithm, now in the Metropolis-Hastings algorithm, if we have the kernel of our target distribution, P tilde x candidate, over the kernel distribution for P tilde for the current location, x tau, each of those times their respective proposals. So in the numerator, it's times the proposal distribution for going from the candidate location, xc, to the current location, x tau. So that's q of x tau given x candidate. That's in the numerator. And then in the denominator, we have the proposal distribution x candidate given x tau, the current location, times the performance at the current location, which is the proposal distribution P tilde at the current location. If that ratio is greater than 1, we will always choose the candidate. We'll always move to the candidate location. And if it's less than 1, we'll have to decide based upon the draw of that uniform random variable. And if it's less than that ratio, then we move to the candidate. If it's greater than the ratio, we stay where we're at. We use this p tilde again because we don't need to know everything about the distribution. It can be very complicated in terms of its normalizing constant. And so as a result, we can still find a good answer in terms of modeling the distribution, the unknown distribution that we're after. We can get a really good answer to that even without knowing everything about the distribution that we're trying to model. If the proposal distribution is symmetric, then clearly we have the basic Metropolis algorithm that we saw on slide 5. Now let's ask ourselves, why would we want to use a proposal distribution that is asymmetric? And the answer to that is that in many real problems, we don't have target distributions that are symmetric that we're going after, and hence the proposal distribution should not be symmetric. For example, consider a case where we're looking to model the distribution of variance. The variance is bounded below by 0. So as a result, we don't want to have a distribution that allows us to search with the entire real line. We want to have it bounded. So it's an asymmetric distribution. It's bounded below by some value, in this case 0, and that causes it to be asymmetric. So we want to be able to search over a broad class of distributions, and this Metropolis-Hastings algorithm allows us to do exactly that. The result of using Metropolis-Hastings for these general cases is that we get a distribution that we find the target distribution that we're after. It is in fact the result of this Markov chain process that we produced, and this Markov chain gives us this invariant distribution as a result of just doing it over and over again, this sampling over and over again, that invariant distribution. And if you recall, we gave the way that we find those invariant probabilities the last time. We said it's these limiting probabilities of being in any given state. And we also saw in a simple little example that we get to those invariant probabilities very quickly. Unfortunately, it's not always that quick, but nonetheless, we will get to those invariant probabilities, that invariant distribution more generally for continuous random variables. We'll get to that invariant distribution through this process of applying the Metropolis-Hastings algorithm to search our space. Okay, a couple comments. Choices for the proposal distribution. Typically, we use either a Gaussian, some symmetric distribution for things that we want to be symmetric, or a Cauchy centered on the current state. If we're not wanting it to be symmetric, then we can use other distributions, for instance, a gamma distribution or something like that, that allows us to not be symmetric because of requirements of the distribution. For discrete problems, we typically use a uniform centered on the current state. Since the samples are not independent, the algorithm does not immediately produce samples from our target distribution, but requires something called burn-in. So we have to let it run for a little while, and then it'll stabilize and start producing what we're after. Estimating burn-in, people have attempted to do this over and over, and there are still ongoing attempts to try and come up with a way to estimate what the burn-in time should be. But the problem itself has been shown to be computationally intractable. So we don't really know an answer to this question. To obtain independent samples, a lot of people feel it's important to get independent samples. And the way that you do it is you run past burn-in, and then you can subsample from the resulting Markov chain. So when you subsample at, say, every nth point, then you get what amounts to independent samples of the distribution. So you can do this, and it's called thinning. It's not always used, but some people argue that it's important to use. Okay, convergence. So convergence means that we've actually converged on this underlying invariant distribution, and that's what we're looking for, the underlying invariant distribution of the Markov chain, which will then be equivalent to our target distribution, P of x. So the parameters that are in the proposal distribution really have a strong influence on how fast we converge, and we can see that with a little example that we'll look at. For a Gaussian proposal distribution, if the variance is small, then the acceptance is high, but this will be a slow random walk through the state space. If the variance is large, then the rejection rate will increase because we will now have to consider many states where the target distribution has low density, and as a result, we're wasting time in those places. So let's look at an example of this. Suppose our target distribution is a bivariate Gaussian with strong correlation between variables. And we'll look at the picture of this on our next slide. Let's let sigma max be the scale of the longest axis and sigma min be the shortest. We'll let rho be the scale of the proposal distribution. So this is what we're using in order to do our search. It suggests that we want to have rho as close to the minimum scale to allow a slow search, so that we'll actually look across this distribution and find the major points. We obviously want to find the maximum, but we want to get a sense of how the distribution slopes. We'll get all of that if we use a rho, which is the scale of the proposal distribution, close to the smallest scale of the target distribution that we're after. The number of steps then to get past burn-in is roughly of order sigma max over sigma min squared. Again, this is a rough estimate. And here's the picture. This is what this would look like. So we have a target distribution shown in blue. We've got one contour from a multivariate Gaussian shown in blue. And this gives you a sense of the largest axis, the axis with the largest scale, and the one with the minimum. And clearly, if we use the suggestion, which is to have the scale of the proposal distribution, rho, about the same as the smallest scale for the target distribution, then we'll actually start searching well across the space of the distribution. Whereas if we make it larger, close to the size of the larger of the two scales, then actually we'll bound around and never really find the complete distribution. And more importantly, we may never find the maximum of that distribution because the scale of the proposal distribution is too large. All right, in the next class, we'll look specifically at how we look at multivariate distributions using the Metropolis-Hastings algorithm, and in particular, a special case of it known as Gibbs sampling.